Andrzej asked me to say something about art and topology. I thought, oh, fantastic. Art and topologies are huge topics, so I can say whatever you want. But obviously, I want to concentrate on something very specific. Namely, I will introduce you to our ideas how to analyze abstract art from the point of view of investigating how people look at such pieces of art. And so this is the output somehow of an experiment which was aimed exactly at this point. So to understand what are the physiological or neurophysiological reactions of spectators when they see or they observe or they look at pieces of abstract art. Okay, so let me start from something like this. These are two paintings. I will reveal immediately or in a few minutes the origin of these two paintings. And okay, they differ somehow. They differ somehow, but how do they differ? Okay, so both are abstract. There is nothing to be said about the topic of these pictures. Okay, they had some titles which are as random as the pictures themselves. So how to differentiate between them? How to say one is such and the second is such? So for me, the first one, this A, is better. This B is not so good. But this is not the point we want to discuss. What was this actually goals and means of this experiment which we performed? So this was identification of features which are important for viewers. Okay, so what do they concentrate? They focus. What they focus on when they look at some pictures, and the experiment you will learn probably a little bit more about this. I would say this neurophysiological part from the next lecture of Shabnam was to somehow measure their reactions. So the reactions were measured, so there are several things which can be done. So, but this we concentrate here are the focusing of eyes, okay, on parts of the pictures or points in the picture. So, but to do this, we have to somehow characterize these pictures, and this is why we use this topological properties, which we believe are important for the people who look at these pictures. So, as I told you, the results of this neurophysiological experiment will be analyzed, or maybe we will learn something from the next lecture of Shabnam. So I want to concentrate on a purely, I would say, topological, geometrical characterization of these pictures as a basis for further comparison with the people's reaction. Okay? And so I decided to do it in very simple terms, just to avoid too much mathematics, but rather to show you what is really important, that we think is important when people look at such pictures. Okay, so the hypothesis was very simple. So in abstract painting, some geometric objects and their features are important. Moreover, this is maybe a weaker part of this hypothesis, that these structures should be persistent in some way. It means that they are really fairly independent on the way you're looking at this. You can focus more or less your vision at some point. So the lighting could be different in different moments. Okay, you can look at from some angle. So, and this should not depend. Everything should not depend on or be not very much dependent on that. How you look at this. So this is what we call persistency, and so the aim actually is to characterize these properties which are interesting and this persistence. So let's start from the persistence. So imagine we are looking at a picture with different resolution, okay? For example, from different distances. And then our basic picture here consists of 5 points, okay? 5 pixels. And these green circles around depict the resolution with which we look at this collection of collection of this 5 points. So when this resolution changes, so with such a very good resolution, okay, characterized by this radius of resolution R1, we see simple 5 points. Okay? When the resolution decreases, so we observe such a structure, which is something like circle, because this is there is a hole inside. Okay, this is one piece, but with hole inside. Then, when the resolution is even smaller, okay, so in the sense this radius is larger, okay. So then everything is in what actually all this reduces to one piece, okay, without any structure inside. Okay, so this R, which we call generally filtering parameter, it could be something else, and it will be actually something else in the future. So what we see depends on this resolution. Okay, so you see that at some resolution, some structures are born. For example, there is such a R at which this hole inside is born. Okay, and then after increasing this R, it is lost. Okay, it dies. Okay, so these points we simply this values of this filtration parameter at which the structure, in this case this circular structure with hole inside, borns. It's the point of it. Yes. So it will be called RB. So this is the point where it is born, and RD is the value of this parameter at which it dies. Okay, and the length of this parameter change between birth and death will be called persistence. Okay, and so, and this hypothesis I told you is that the more persistent structure are more important for the image. Okay, because they could be visible with, for example, in this case, with different resolution. Okay, the second, so we know what is persistence, okay, at least in our approach. And the second thing is how to characterize these properties, geometric as I call it, or rather topological. So here, what we use, so in technical terms, is algebraic topology, homology theory, but in fact it's quite simple And that's why I decided to explain it without actually mathematics at all. But in fact, this is exactly what stays behind this term topology in this case. So we have two sets of figures, okay, A and B. How do they differ? So first, what they have in common? No? They have in common that they're both, in a sense, consist of two pieces, okay? But in this case, these pieces are separate, okay? They are not joined. And in this case, they are, with this 1 point. The second difference is that in this case, one of these triangles, one of this figure is, as I called, empty or hollow, and the second one is solid. Okay, so this gray part also belongs to this. Well, here in this case, both are hollow. Okay, and in fact, these are the most important features which we can use to differentiate shapes, or at least the simple shapes, for example, triangles, but not only triangles, and on two-dimensional surfaces. Okay, everything is two-dimensional. Obviously, this part of mathematics, homology theory, okay, deals with arbitrary dimension, but what we are interested in is 2 dimensions. That's why it is so simple. So, how to differentiate between these two triangles in, I will say, such an algebraic manner? Everybody sees that there is a difference because one of these triangles is empty. The second one is has also this interior. Okay, so the characterization which is used in this homological analysis could be summarized as follows. So the first, both triangles have the same sides. Okay, these are these segments AB, BC, AC, or CA. So in the solid triangle, this boundaries, the segments, okay, the sides form a boundary of a region which also belongs to the triangle. Whereas here, they do not form such a boundary because this interior does not belong to the triangle. And this is the actually main difference. So I would say that this homological analysis deals with the relations between boundaries and interiors. Okay? Okay, so this is what I said. This formalization and study of such observation is the matter of this homology theory, and it provides an algorithm, okay, to calculate just by, as I called it today, traveling along the segments, the sides of the figures, and checking whether there are boundaries of regions or not, to give two basic characteristics of this plane structures, which I mentioned before. So whether there are parts which are disconnected, or whether the figures which we observe, the interior also belongs to this figure or not. Okay? So in a sense, we can, using this ideas, this algorithm, we can calculate number of unconnected parts and number of holes. Okay, And the result of this are two numbers, which are called Betty numbers. This beta 0 counts the number of disconnected parts in the structure, and beta 1 the number of holes. Okay. So now we can characterize these differences for our triangles by this in algebraic way by these two numbers. Okay, this is the number of holes. S is this empty triangle. Okay, so the number of holes is 1. The number of pieces is 1. Okay, sorry, the number of pieces is 1. The number of holes is 1, and the second one. The number of pieces is 1 because it's a single triangle, and the number of holes is 0. Okay? And for the more complicated, for example, this collection of two triangles in two positions, different positions, we have for this arrangement we have beta 0 is equal to, because there are two separate parts, they do not connect one to another, and one of them is empty. Okay, so there is one hole. But in this case, we have one piece, because they are somehow connected, glued here, and the number of holes is 2. So both the structures are characterized by two numbers, these two Betty numbers. Okay, so how to apply this to our pictures, our paintings? So first, we imagine that this is actually the experiment. It was so because people who are investigated from the point of view of the eye movement and so on, they were confronted with this figures on the screen of the computer. So in fact, you can say that we pixelize these pictures. So they are simply arrays of pixels. Okay, you can do it by converting also to the grayscale, or you can investigate different color channels. Actually, the results were dependent on that, so that's why it's not so important here. Okay, so each pixel, which is represented here by a square, as it is in fact, okay, is characterized by this. In this case, for example, imagine that this is intensity of gray. So then this numbers here are intensity of gray from 0 to 1. Okay, and imagine they are looking at this picture by the filters with different permeability. So it means that the good filters transmit all this, so you see through the good filter nearly everything. Okay, for the bad filter only this which are brightest in a sense. So this mixture of gray is the lowest. Okay, so let's now see what happens. So this filtering again is something to measure the persistence. Okay. So we will use this method as I described. So the counting of number of holes and number of disconnected pieces for this case, and we will use several characterizations here, which are named here on this transparency, which are called barcode, persistence diagram, and petty curves, and which I will explain in the next picture. But now I can say, so barcode is a set of line segments of the length which corresponds to the persistence of particular structure, for example, particular hole. Okay? It appears at some resolution or some filtering parameter, and then disappears. So the length is this persistence, as you remember. Okay, so this is the first presentation. Actually, all this kind of kinds of methods of presentation of the results, they are actually, they present the same, but in a little different setting, which would be more better or worse analyzed, okay? So there is a persistence diagram. So this is simple two-dimensional diagram of these points B and D, okay? So there are coordinates. And Betty curves, so these are numbers of objects of unconnected parts, which will be denoted by dimension 0, and holes, dimension 1. So notation is connected with this topological. Okay, so let's see how it works in this particular, for this particular structure I showed you. Okay, so this is this shape, okay, with different intensity of grays for each pixel. And let's imagine that now we are looking through a very, I would say, restrictive filter, so we see only those which are very bright. Very bright, it means that the number which is in each of the square is the smallest, in this case 0.1. So what do we see? So we see that everything consists of two parts. Okay, so this is one part. This is this larger second part. So they are disconnected because we do not see this pixel. And there are two holes because we do not see these two pixels. Okay. So at this moment, at this value of the parameter, the Betty number 0 is equal to 2 because we have two ports, and Betty number 1 is equal to 2 because we have two holes. Now let's imagine that we are looking at the resolution. So now we see also the pixels, the filter is less restrictive, and we see also pixels which are a little bit brighter, okay, a little bit, okay, dimmer, I would say. So this, which are 0.3, okay. So what concerns the number of parts, nothing changed because we still do not see this one, but one hole vanished, okay. So at this point, the Betty number 0 will be 2 as previously, but Betty number 1 will be 1 because there is only one hole. Okay. Then at point 4, okay, this is also visible. So now there is only one part here present, but with one hole. Okay, so then Betty number 0 is equal to 1, Betty 0 is 1, and Betty 1 is also 1. And finally, this is we see everything. So this one piece, no holes. Okay, and now these are these methods of presentation. This is a barcodes. These are barcodes. So these are segments with the length of the persistence of each of the structure, okay? So these are 0-dimensional, so this is number of pieces, okay? So between 0,1 and 0,4, there are two pieces, okay? Then there is one piece only, okay? For dimension 1, the number of holes from 0 to 0.3, there are two holes, yes, and then one hole survives until 0.5. This is the same data which are presented on this persistence diagram, which means that we put here is B, so verse, and here is D. Okay, so you see this red correspond to this red, this green to this green. Now you transform it a little bit, rotate it by 45 degrees, and build such pyramids on this. Okay, so see, so just connecting this to the diagonal. So this is something which is the most important for us, which is called persistence diagram, and these are Betty curves. Okay, so you see that the number of holes changes from 2 to 1, The number of pieces changes from 2 to 1. Number of holes changes first to 1, then to 0. Okay. Okay, so now let's see what we get. Sorry. Okay, it should, oh, yes. And so this analysis applied to these two pictures. So as you can expect it, so in a sense, this A picture is more complicated. So you see this clearly on all these diagrams. So these are these landscapes. Okay, so these are these pyramids built on that. So you see a huge difference between it. These are these barcodes, okay, for the structures of 0 dimension and 1 dimension, so number of parts involved. And these are Betty curves. Okay, so we characterize somehow these pictures. Then you can really differentiate by these numbers between the two. Okay. Now I can show you that these were somehow pictures taken from two samples. First sample is this one, and these were the painting which were committed. We were painted by an artist. Okay. Okay, so this is this guy's picture. And there is another sample of 12 pictures, which are actually produced by computer. Okay? So I think at the beginning, my colleagues, the neurophysiologists, had a mischievous goal to see whether people can differentiate between the real art and the artificial. But I think this is pointless, because you can now teach the artificial intelligence networks to produce whatever you want. But nevertheless, okay, so fortunately there were differences we do not need to somehow be ashamed, especially for well, meeting the artist who produced these pictures, okay, that her pictures are not so as good as this. But this was not the point. I think that the fact that these pictures were definitely poorer and less interesting actually was fortunate for us, because we could then identify, as you will learn from Shabnam's lecture, the features which are important when looking at it. So my point is that we could somehow characterize in this few methods, okay, using diagrams, barcodes, or whatever, on this persistent landscapes, to differentiate between the pictures. And I show you these two samples just to say that it is also seen in the averages of that. Why I wanted to say it. Okay, so these are the average landscapes of these good artist pictures, and this is average landscape for this computer-produced pictures. Okay, average over the sample of these pictures. Okay, so
what's the meaning of the color?
Too complicated to say at the moment. Okay, so, no. Yes, someone will explain. Okay? This is maybe not this is at this moment this is not so important. Okay. Okay, so it will be fair to say that definitely we are not only ones who want to somehow characterize, I would say, numerically the features of pictures. Okay. And so we try to compare this with several other approaches, which are mostly statistical approaches. And the problem with statistical approach, from our point of view, is a little bit similar to Andrzej yesterday said about statistical approaches. Okay? Statistical approaches have this, I would say, shortcoming that they are statistical. Okay, so I will explain you what does it mean for us. Because for us it was important that we can identify not only this object, but in a sense where these objects are. Okay, all the other things all the other measures which we proposed, which we found and we compared, were statistical. So what is the idea of such a statistical approach? So image, as in our case, is a rectangular array of pixels. Okay, and to each of these pixels there is ascribed some value. Okay, it could be gray intensity, it could be intensity of green, blue, red, or whatever you want. And then, so I will try called feature descriptor. And then the first approach, if you have this descriptor, so the statistical measure which you produce out of that was a standard one usually. So the only idea is to invent good descriptor, but you simply plot a histogram of the values of this f of xy, so f for each pixel, and then you can somehow normalize the probability distribution, and that you can do whatever you want with that. Okay, for example, you can calculate Shannon entropy, which somehow Shannon entropy measures the uniformity of the distribution. So you see that this is really average over the picture of something. Okay, so what kind of this, which I like very much, was something which we missed in our approach, mostly because I don't think that anybody knows how to do it properly and effectively when you have more than one feature ascribed to the pixel. But there is one which I like, which somehow takes into account the fact that there's also color in the picture. Okay, so this is the schematic plot of the so-called color space, which is roughly three-dimensional, but this is not RGB as you know, but rather something which we can say hue, saturation, and value. And hue is, I'm a physicist, so from the physical point of view, the frequency of light, okay? And saturation is admixture of gray. So this is admixture, or the same as admixture of complementary hue. And the value, this admixture of white and black. Okay? So you can see on this picture. So we have actually 3 coordinates for each point. And the idea, and this is the citation, I can be more specific. So there you have this primitive description. You calculate the gradients of them. So you calculate how do they change from pixel to pixel actually. So this has this three vectorial values, okay? And then this feature description which you use is maximum of them two, okay? And complexity is then defined as something like this, okay? So this is also a statistical measure because this is the sum over all of these things. Okay, so there is something which is called anisotropy. You use also this gradient, okay, gradients of changes, and then see how it depends on the angle, and then you calculate the cumulative distribution of that. Okay, so taking into account this probability of being in the angle, say, weighted by the intensity itself, in a sense, and then you calculate something like anisotropy. So this is also a statistical measure. And for an image that is anisotropic, so it's dominated by lines of approximately the same direction. Okay, so this will be somehow visible in this measure because this variance will be small. Okay, there is something which is called self-similarity. you know what the self-similarity from Andrzej lectures yesterday, okay? And so the structure reappears on the lower level. So you divide your paintings into segments, and then compare them with the whole, also in a statistical manner. Formulas are given here, which are not so important, but then you have to somehow compare the result for the whole picture and for the parts. So you have to compare this probability distribution, and this is what is used, is such a distance between two histograms. Okay. Okay. Then you can do the following. You can filtrate this paintings or picture or whatever it is using a family of filters which somehow detect the linear structures in such paintings. So lines, okay, visible lines. So these are called cover filters. There is Fourier slope, which is the two-dimension discrete transform of our feature descriptor, this basic feature descriptor, and then averaged over the directions, and then calculate, and then these are the slopes. Okay, so this was somehow this was used to differentiate between different types of pictures, for example, photographs, paintings, and so on. Okay, so this what I wanted to say, that I do not claim that our identification of features, of geometric features, or whatever features of pictures is the best, but it is definitely not bad. So it usually performs better than all the statistical properties, even if we make a statistical measure of our approach. Namely, these are the feature which we extracted from our result was the total area under the persistent landscape. Okay, so this is also a statistical properties because you average over everything. And even this usually works better than other. Okay, so this edge density. So the criteria is in this box is definitely in different position than this box. These are fake pictures made by computer. These are artist pictures. So if this box is visibly in different place than this box, I will not go into details. So then you say that you can discriminate between these groups. So as you see, in our case, it is very good. Discrimination is very good. In others, maybe this one and this one are a little bit better than others, but also worse than ours. Okay, so this is, so as I told you, so I concentrated here on the features, and you will see what is the purpose of this from Shabnam lecture. Thank you very much.
Right on time, with 1 minute to spare. Perfect. Okay, are there any questions? Gregor.
So I do image statistics. So I was wondering, you said that with your method you can say where the objects are in the image.
How to you want to know how do I know where they are? Because you can see when this particular features appear, when they are born. Okay, when you change your filtering parameter. Yeah. So at some stage they appear. Okay. And you can identify the places also on the picture where that happens, okay? Where this.
But in the end, you get a measure. But in the measure,
yes, that's true. That's true. It was not clear here, but you can, okay? So now we'll show you.
Okay.
Okay, but you can identify the moment when it appears in this particular part of the. You can imagine, okay? You change this. Sure. And then there is one pixel, or usually there is a group of pixels which closes the loop, okay?
Okay, I got this, but it's not really in the measure there.
No.
Yeah. Okay.
Yeah.
Maria?
How do you make the painting selection?
Pardon?
The paintings. How do you select?
Oh,
There is a criteria that you
the selection. So the sample which was painted by an artist, it was selected by her, okay, because she painted them. And the pictures which were produced by computer, it was we used such a, I would say, available big gun network, which is a generative adversary artificial network, okay, which actually were constructed to produce realistic pictures, okay, in fact. And it works that there is roughly, there are two networks, one produces the picture and the second discriminates whether it is really this funny cat which we wanted to produce or not. But we disturbed this production moment of this to obtain these abstract pictures in a sense. So they are somehow generated from the what the network knows about what on the realistic pictures, but somehow perturbed to make it abstract in a sense. Then we produce something like 4,500 such pictures, and we to choose 12 to compare with this other sample, and it was done by calculating also some averages. So average distances between this real pictures and this which we produce. Okay, distance is defined in a various way, but in a sense by comparing the intensity of colors. Okay, at each pixel. Okay, and then you can calculate some distance between the two, and then minimalizing this distance. So we choose 12, which were so as close as possible. So this was the way.
But of course the details of your results in comparing the two sets depend critically on the program that produced these and on your selection criteria.
Obviously, and as I told you, so we are lucky enough that these paintings produced by computer were so bad, because
yes, you were lucky
because then we can identify these features which were important, as you will see from the point of view how people looked at them. Okay.
I'm just putting a grain of salt, but you agree with the grain of salt.
Yes.
Alan.
Very interesting. This idea of a hole seems a bit sort of on-off and a bit sort of round. How to do sort of I can imagine really complicated holes. Really
no, hole is an entity with a simple and basic entity. It has no complication in itself.
Well, I can imagine how you say. Well,
but can be hole in hole and hole in hole and something.
Well, let's take a fern. I mean, how does a fern score on your metrics?
Good question. No.
You'd have to do this,
yeah.
Right? I mean, you'd have to actually run this code.
I mean,
You can answer it. Maybe it's your
meaning value from this research. We can subjectively look at a Kandinsky that generally subjectively the art scholars or artists or population consider a masterpiece. And you might run this analysis on that and find out that no, you wouldn't do that?
I can do this, okay. We did it for several painters, for Kandinsky, for Rothko, for I don't remember, so for some. And you can, as I say, you can produce some constants of non-constants, okay. This definitely was not our aim to somehow measure some aesthetic value or whatever. Moreover, the experiment which I think I'm not a specialist neither in art or in perception of art, but I believe that to really perceive whether this is good or not, you have a very long time to look at this of this picture, okay? Then you have this secondary association and so on. The experiment actually measured the reactions of the people in very short times, okay? So this was at the first site, where they look at the first site. And this was our, okay, this is what we wanted to investigate.
So my question is, for the objects or the artworks that had, we'll say richness, you know, like stronger hue, many holes, those tended to be more compelling. I'm assuming people would be gravitating toward that. And so you can use that as a tool to predict if this painting is successful or not.
Probably yes.
Okay.
Probably yes.
By the way, is there any reason to look at higher Betty numbers?
This is very hard to imagine how do you construct this higher complexes here. This is very natural, okay, because this is two-dimensional, okay. So in a natural way, actually what is used, I didn't mention, is technically so-called cubical homology, okay. So this is like simplicial homology in the case that you have simplices on different dimensions, and that they glue them in a proper way to hide. And this is the same, but the simplices are simply the unit squares and the construction of that. Okay, you can have unit cubes, but in 2 dimensions you cannot imagine what is the third dimension. So you can do it somehow, abstract idea how to encode this in some higher dimensional spaces, but I think that there is nothing more than 2 dimensions here. Okay? In nature.
Go ahead. So generative AI is notoriously bad at counting. You know, giving wrong numbers of fingers, etc., etc. Is there any way to get something like persistent homology, embedded within generative AI, so it can actually count the number of things it's generating? And
I hope so.
make that
So
plausible?
I never thought about this in this terms, but yes. So I'm a believer in homology theory. So I would like to also apply it to music.
Try and address some of the points that people have come up with, because I can show some more details about.
All right. So let's thank Marek.